Hello, I'm Doug Montgomery. I'm the instructor in your course, and I'd like to welcome you to our November 2024 Fireside Chat. Uh, for those of you that are relatively new here, this is something that we do on a monthly basis. I always have a guest speaker who talks about some topics that I think will be of interest to you. This is a very good time for you to think about asking questions for our course. And your question can be really be anything. It can be about the course content. It can be about the guest's topic, or it can be something that you're interested in doing. You may be trying to use experimental design for a specific situation. And if you have a question about that, we'll try to answer those. If you're on Coursera, um, these fireside chat recordings are posted. They're recorded and posted in the course. You'll find them in your resources tab of your course. A couple of quick reminders, please. Please keep your microphones muted and your cameras off during the session, because that way we don't have any extraneous noise or other potential disturbances like your dog barking or something like that. That would be my dog always barks when I'm having a Zoom meeting at home, so I understand that. If you want to submit a question, either to me or to our guest, the way to do this is to use the chat function on the Zoom menu, and you don't have to wait until the Q&A session begins. You can input that question any old time, at any point during the session. And if your question doesn't get answered during our hour here, we will try to respond to it in Coursera for those of you that are enrolled in the course. So that's sort of about the background about how we're going to do this. And now I'd like to introduce our guest. Our guest today is Jon Stallrich, who is an associate professor in the Department of Statistics at North Carolina State University. He received his Ph.D. in statistics from Virginia Tech in 2014. I got my Ph.D. at Virginia Tech too, although it wasn't in statistics and it wasn't in 2014. Okay, it was in 1969. Okay, Jon's interests include design and analysis of screening experiments, computer experiments, online controlled experiments, functional data analysis, variable selection. He's got a wide range of really interesting things that he's interested in. In 2021, he and his co-authors were awarded the American Statistical Association's Statistics in Physical Engineering Sciences Award for their paper, Optimal EMG Placement for a Robotics Prosthesis Controller with Sequential Adaptive Functional Estimation. He's currently working in an area that I'm strongly interested in. It's identification of new screening experiments that allow for model-free estimation of the error variance and developing an optimal design framework for penalized estimation. So I am very interested in this talk, and I'm really pleased to welcome Jon to our fireside chat.
Well, thank you very much for the invitation. A lot of the co-authors that I've been working with in the past have been participants in this fireside chat, so I'm glad that I finally get to join the club.
Was super glad to have you, Jon.
Thank you. So I'll be giving a brief presentation on a recent paper that I had with my former PhD student, Michael McKibben, who's currently at the Johns Hopkins University Applied Physics Lab. And it's about optimal designs for two-stage inference. There's really two main parts of this paper, but I'll just be focusing on the first one because it's the easiest to kind of wrap your head around. And so it's mainly talking about how to come up with good designs for screening experiments, which people have been looking at for many, many years. But the basic idea, again, just to ground us all, is that we're manipulating k different factors to determine which of those really drive most of the responses variation. So we're assuming going into this that not all of them are going to be important. And so I want to figure out, first off, which ones do I need to focus on mostly, and then maybe I care about building some good predictive model after that. So to simplify things, we'll just focus on the case of where we have maybe numeric factors, and they're standardized to be between -1 and +1, as is commonly done. And we'll just focus on two-level categorical factors, and their settings are just also +1 and -1. So we can represent our design using this design matrix where we have n runs and k factors. And each row of this design matrix is telling us what the settings are for each of the k different factors. When we do our analysis, we typically assume that there may be some low order main effects that we have in the first part here. And then maybe using some second order Taylor series expansion, we think there may be some second order terms like bilinear interactions here, or even quadratic effects. And so we can represent that in matrix notation as just x1 beta 1 for the intercept and linear main effects, and then x2 beta 2 for the bilinear interactions and the quadratic effects. Now, there's lots of different ways that you can do the analysis. The challenge with this, though, is what we're trying to do is trying to learn about what this model is with using as few runs as possible. There can be quite a lot of terms in this model, and trying to estimate all of them can be overwhelming. And honestly, it could be a waste of time because we have these effect principles that tell us that we could have a model this big, but usually there's a lot of sparsity going, and where only a few of these effects are really important to the model. So we don't want to use too many runs to try to figure that out. There's lots of different ways that people have talked about analyzing these types of experiments. I'm going to be talking about a two-stage analysis that's become popular, especially with these definitive screen designs and these OMARS type designs, where in the first stage, you'll just be fitting a main effects model. And we'll be doing our inference on the K main effects using t-tests, which we all learn about in basic statistics and regression courses. Then in stage 2, I'm going to take those effects that I find to be important, and I'll do some sort of model selection with maybe like BIC or something to kind of pick the best model. So this talk, I'm mainly going to talk about what we'll do for finding an optimal design for stage 1. The paper does go into the stage 2 criteria. So the stage 1 analysis, doing t-tests is equivalent to looking at confidence intervals. So constructing confidence intervals for each effect and looking at whether they contain 0 or not. So when I fit the main effect model, I have this estimator and I have this variance expression. And so our confidence intervals for all of our main effects are going to come from the jth diagonals of this x1 transpose x1 inverse matrix. And I'll call those the design variances. So that's what I mean by VJ. Now, technically there is one for the intercept, but we don't care about doing inference on the intercept. We just keep it in the model. So we say a factor J is important if its main effects confidence interval does not contain 0. And here's the familiar expression that we all have seen, I think, at some point for how to construct that confidence interval. We have our estimate plus or minus the margin of error, which is a combination of 3 different things. We've got the T critical value, where the G here is indicating our degrees of freedom used to estimate the variance sigma squared. I have my estimate for the standard deviation, and then I have the square root of my design variance. So we should ask ourselves, what makes this, or what would make this a valid inference tool, and how can I choose my design to maximize the inference performance? So there's different components to this that we need to talk about. The first one, which is what traditional optimal design solely focuses on, is trying to find a design that makes these design variances as small as possible. So for the type of designs that we're talking about, it's well known that the lowest possible value that you could get is 1 over n for the design variances. That corresponds to what we call an orthogonal design. And so if we can find an orthogonal design, presumably that's the one that we would want to do if this is all I cared about. Now, how this helps us with inference is that minimizing the VJs creates tighter confidence intervals, and so should maximize the power for detecting which effects are important and be able to decide which ones are unimportant. But in reality, what we're probably going to have is some of the VJs are going to be unequal and they're going to be greater than 1 over n potentially. So our design goal for an arbitrary run size is that we should be trying to push all of these VJs as close to the minimum value as possible. Now, like I was saying, an orthogonal design or orthogonal array does satisfy this, but those only exist when n is a multiple of 4. So 4, 8, 12, 16, so on and so forth. So any other n between that, I wouldn't be able to do this type of design. So for a general n, we can use what we call a variance-based criterion. And the two most popular ones are the D criterion and the A criterion, where the D minimizes the determinant of the design variance matrix, but the A criterion minimizes the trace of them, which is looking at the sum of all the VJs. Now, looking at these two, it more clearly makes sense to me that the A criterion is more directly trying to minimize those VJs. The D criterion is doing it as well, but it's not so obvious to write it out. And I have a recent paper in Technometrics where I actually show that a lot of times the optimal designs are the same under these criteria, but when they're not, the A optimal design tends to do a better job of minimizing these VJs. And so that's what we're mainly going to be using that idea in this presentation. Let's talk about this estimate beta j hat. For the interval to be providing valid inferences, what we need is for that to be an unbiased estimator for beta 1. But what we end up having is a potentially biased estimator, which involves this linear combination of the second order terms that I haven't fit in my model. And so the matrix I've highlighted in red, that's called the alias matrix. And so our design goal is, I know what x2 could potentially be. Is it possible that I could pick a design such that that alias matrix is close to 0 or even exactly 0? And in some cases, you can do that. And what people will do in general, one strategy is to just focus on orthogonal arrays and then do a secondary selection among those orthogonal arrays that uses some measure of aliasing, like resolution, minimum aberration, or general minimum aberration. But I don't like that approach because it's kind of doing this two-step sort of optimization where you first focus on minimizing the VJs, then you talk about minimizing the aliasing. There's other criteria out there that kind of balance the two criteria simultaneously, like these Bayesian D and A optimal designs, which require you to specify some sort of prior on the second order effects. And then there's a more recent paper by Brad Jones and Chris Knockstein called Efficient Designs with Minimum Aliasing. And this actually was a motivating paper that led them to discover definitive stream designs, if you've heard of those. And that in turn led to the discovery of a more general class of such designs called Omar's designs. So what I want to talk about now is the last component, which is often overlooked, and that's the variance estimation part of this t-test. And so the sigma hat squared is usually calculated using the residual sum of squares from the main effects model. And so this px1, that's the projection matrix onto the column space of x1. And then g would then be the difference in n minus the rank of x1. So for this to produce valid inferences, what we want, or what we need really, is for this to be an unbiased estimator of sigma squared. And we would like the degrees of freedom to be relatively large because that makes this critical value smaller. But what we're going to have is a biased estimator, in fact, an inflated estimator for what sigma squared is, based off of the different, or how many significant effects there are in those second order terms. And there's nothing that we can do to reduce this doing some special cross products between x1 and x2, which we could do with aliasing. So what's our design goal? How can I make this a unbiased estimator? Well, what we need to think about is the entire largest possible X model matrix. And we can carefully choose our design so that we redefine G to be n minus the rank of the entire X matrix. Now, this is essentially going to be sacrificing our ability to estimate some of those second order terms, but I'm willing to do that for the sake of being able to estimate variance. And then we get this new estimate for variance with when I'm assuming that this is the largest possible model that I could have will be unbiased for what sigma squared is. And so there's two ways to make this large X matrix rank deficient, which is essentially what we're trying to do here. The first way is to replicate rows in that design matrix, which is replicating design settings. That's often called a pure error estimate of variance because I can use the responses from those to estimate variance without having to specify what the true model is. I'm running the exact same design scenarios. Their expected value should be exactly the same. So this was actually an idea from Gilmore and Trinka in 2012 that kind of motivated a lot of future papers, including this one, where they looked at kind of those DNA criteria and they required some number of pure error degrees of freedom. In this 2017 paper, they did the same idea, but used a Bayesian D-optimal design in an effort to try to balance these three aspects: design variances, minimizing aliasing, and estimating variance. But another way that we can do it is from a so-called lack of fit estimation that was used in this Jones and Nachtsheim 2017 paper, where they augmented a DSD with extra columns to make the X matrix rank deficient. And so it's not through replication, but it's through something that they call fake factors that they make orthogonal to the large X matrix. So what we're basically faced with is a multi-objective optimization. I'm trying to balance all these three things. I have techniques that can minimize variances, minimize aliasing, and give me unbiased estimation of variance. But I want to try to do all those things simultaneously. And so the way that I'm going to do that is by looking at what I call these expected confidence intervals. And so what I mean by an expected confidence interval, I mean I'm going to look at the expectation of the endpoints of a confidence interval. And so when I take the expectation of my estimate, I get the beta j I want plus the potential bias, as AJ transposes the jth row of the alias matrix. And then I've got the expected value of my variance term, or my standard deviation, I should say, here. And then I've got another component, the number of degrees of freedom that I have, and then I have the design variances. Now, what I'm going to try to do is for each of my main effect confidence intervals, I want to minimize the expected confidence intervals maximum deviation from the truth, which you can show easily as just this expression here, which just takes the absolute value of the bias. And so if I'm able to minimize these maximum deviations, I'm doing that by achieving all the three goals simultaneously. So there's a couple of technical points that I need to bring up. If I take the expected value of the standard deviation, I'm going to have a sigma component, which means I would have to know what sigma is to be able to optimize this criterion. So we're going to re-express this as intervals for the signal to noise ratio by dividing by whatever sigma might be. And so then I get this expression here. And we show in our paper that the expected value of the ratio of our estimate of the standard deviation and the true standard deviation is not 1. It's actually this term here, which depends on the degrees of freedom. It's pretty close to 1, but it's a little bit more inflated than that. And this is the gamma function. So let's cut down some of the notation. Let's just define C alpha G as this expression here. And that makes our maximum deviation this expression. Now, finally, I need to talk about the first part here, because in order to evaluate this, I might need to know what beta 2 is, which I'm never going to know in practice. So we're going to borrow some of the ideas from the Bayesian literature, and I'm going to give sort of a prior for the signal to noise ratio of the second order effects. And I assume they're normal 0 with some variance tau squared. So the smaller I make tau squared, I'm saying I don't think there's a lot of second order effects that are in there. The larger I make tau squared, I'm saying I'm really concerned about there being second order effects. And so the expected value of this term here, you can show involves tau squared and involves the alias component right there. So when I'm going to be evaluating this criterion, I just need to sort of treat tau as a tuning parameter for how concerned I am about those second order effects being included in the model. So we finally arrive at the expected confidence interval criterion, which is trying to minimize the average maximum deviations. So this is just those three different components that I talked about. So there's different ways to minimize this for a given tau and a given alpha confidence level that I'm interested in. I need to balance minimizing aliasing, maximizing degrees of freedom for estimating variance, and minimizing design variances. And so I'm just going to let a design search algorithm try to find a design that minimizes the criterion. I'll do this across a couple different values of tau squared and alpha, just to sort of generate a variety of different designs. I can't go into details about this, but it's actually non-trivial to try to force a design to have a certain number of lack of fit degrees of freedom. I could do that easily with replication. I could just say, keep replicating this many rows. But forcing a design to have a certain number of lack of fit degrees of freedom is quite challenging in general. That's, again, the beauty of this search algorithm. It might stumble upon something like that, and those designs would be highlighted. So with these kind of variety of designs, I can then sort of inspect them one by one to kind of get a better gauge of how the trade-off is working between the design variances and the aliasing. So let me demonstrate this with this reactor experiment from this Box et al. 1978 paper. This is actually an example that was given in the EDMA paper by Jones and Nachtsheim. And the idea was that reactor experiment was originally run as a 2 to the 5 experiment, so 5 factors in 32 runs. And when they did the analysis of the full data, what they found was actually only these 3 of the 5 factors were important, and just these 2 two-factor interactions were needed. So the true model is actually quite sparse. And so let's ask ourselves, could I have reached similar conclusions had I run a 12-run design instead? So cutting out, more than half of the runs that they needed to use. And so I'm going to compare 4 hypothetical designs: a non-regular fractional factorial design, which mainly focuses on minimizing design variances; a Bayesian de-optimal design, which balances design variances and aliasing; an EDMA design, which is kind of doing the same thing, but with a different technique; and then finally, our design, which does variance aliasing and also looks at degrees of freedom. So here's a summary of the table. The first row is showing the estimates under the full factorial analysis. So we're going to treat these as sort of the truth, the target that we're trying to hit with our other designs. So this first chunk of numbers here, that's the estimates I get from the 12-run designs. The next ones, I show the design variances for the different designs. And then down here, I'm showing the aliasing for the different main effects. So let's focus on the first 2 designs here. Immediately, we can see the estimates are way off in a lot of cases from the target. This is negative 0.688. This is way off in magnitude. And it happens in a lot of other cases as well. The cause of this can be seen immediately from the aliasing. This aliasing amount is quite high. We'd like these to be 0. And that's what is causing the estimates to be way off the mark. The benefit, though, of these 2 designs relative to the other ones is that their design variances tend to be smaller. And that's what we would expect, because that's what these criteria tend to focus more of their attention on. If I look at the 2 other designs, which are better at balancing the 2 criteria of variance and aliasing, we can see that their estimates are much closer to what they are under the full factorial model. And they both have 0 aliasing, which is what's kind of leading to those estimates performing well. But looking at just the design variances, you would see that the EDMA design has smaller design variances almost in every single case, this being the one exception. So based off of this description, you might say, oh, well, the EDMA design looks like it's going to be performing better. But again, we haven't talked about actually doing inference with t-tests. And I found out that the EDMA design in that paper actually had a 1 degree of freedom lack of fit for estimating variance. So if I were to do traditional inference, I would have to use, and I'm doing like 90% confidence intervals, this is the critical value that I would have to use, which is 6.31. Our design has 2 pure error degrees of freedom. And so my inferences would use this critical value, 2.92, which is 3 times, or I guess about half as small as the one under the EDMA design. Here's a representation of our design, and I want to break them up into different pieces. These are replicated runs. This is another set of replicated runs. And these runs are the mirror image of the runs down here. We call those a foldover. Every other pair that I show below it is also a foldover. And it's this foldover pattern that actually gives us zero aliasing between the main effects and the two-factor interactions. So as I was saying, while the EDMA designs have smaller design variances, the ECI is preferred because that one extra degree of freedom for estimating variance significantly reduces their critical value. And so the takeaway from this is that estimation of variance, getting unbiased estimation, should be treated just as important for screening as it is for minimizing design variances and minimizing aliasing. Now, I do want to share before I wrap up a new construction technique that I came up with about a week ago that will tend to create really good designs under this ECI criterion. And a lot of it is motivated by the original definitive screen design paper. So again, let's suppose that the X2 matrix is just comprised of those bilinear interactions and the quadratic effects. And that's the same assumption made with DSDs and OMARs. So here's the setup. Let's say the total number of runs that I have is even because I want to do this foldover technique. And that is greater than 2 times k plus 1. The idea is that you first construct an A-optimal design for half the number of runs and just focusing on the main effects. The caveat, though, is I'm not just doing any A-optimal design. I'm requiring one of these two conditions. The first condition could be I require 2 of the rows to be replicates of each other. This is how I'm generating pure error degrees of freedom. The other technique is that you just require 2 rows to be foldovers of each other, meaning one is the negative of the other. And then with that n over 2 run design, you then fold over that whole design to get your n run design. And so some properties of this is you're going to get always 2 pure error degrees of freedom, and you're going to get at least 1 lack of fit degree of freedom for estimating sigma squared. You're also going to get 0 aliasing between the main effects and the second order terms, both the interactions and the quadratic effects. And so I actually recently did this for a collaborator at NC State, and they had 8 factors, and they said they could do 20 runs, which just barely meets the criterion that I gave. And they actually said they don't care about quadratic effects, so I'm just going to assume all the x's are plus or minus 1. Here was the optimal 10-run design that I generated. It took me about a minute to do it. Here's a bunch of plus and minus 1s. And then I take a folder of that to get the remaining 10 runs. And that's my 20-run design. My 2 pure error degrees of freedom come from these 4 rows. If you look down at the bottom, this is my replicated row. And then when I do a fold over, I get another pair of replicated rows. I also get 1 extra lack of fit degree of freedom. That's harder to explain where that comes from. And so my total degrees of freedom for estimating variance is 3, which is usually more than adequate to get a pretty good confidence interval width. My main effect variances are actually pretty close to the optimal value of 0.05. I'm not too far off. So I'm sacrificing very little in terms of design variances. And looking at the pairwise correlations between my main effect columns and my two-factor interaction columns, I get 0 correlation, which means I get 0 aliasing. So this design is a very strong candidate for minimizing the ECI criterion. And it's a technique that can be constructed very, very quickly. So just to wrap up, I think that we should, based off of kind of the past decade of research, optimal design should always be thinking about not just estimating the parameters in the mean part of our model, but also always being able to estimate sigma squared, because we're always going to be doing some sort of inference at some point, and you need that estimate to be able to do that properly. I showed you this ECI criterion, and I talked about how it balanced those 3 objectives: minimizing design variances, minimizing aliasing, and ensuring an unbiased estimate of sigma squared. And I also presented what I consider to be a pretty brand new direct construction method that works pretty well. Now, the other half of the paper, which I didn't go into, also describes a secondary criterion that we can use on these designs to optimize the stage 2 performance, which is looking at, model selection for BIC, but that's kind of beyond the scope of this talk. It kind of takes a long time to describe it. If you're interested in it, just search for this title in Google, and you'll see 2 things pop up. You'll see the JQT paper that was recently accepted. You'll also find an archive version, which is free, which you can read. But if you go to the JQT paper, you'll see that there's R code available for you to actually generate these types of designs and to do the full stage 1, stage 2 analysis automated for you in R. Okay, that's it for my talk.
Very nice. Um, you didn't really go into the construction method, and I don't want to spend a lot of time with that, but just in general, is it are you using some sort of coordinate exchange scheme to do that?
For oh the yeah, I'm using a coordinate exchange algorithm.
Okay, because
Yep.
that would seem to me to be a logical kind of way to approach it.
So it is a little bit more complicated than that. Let me stop my sharing.
Yeah,
Um,
I'm sure my brain is oversimplifying here, but
right. Well, I mean, it works for the most part. The complicating feature though is that when we're doing this, we're saying I need to make sure that I have this many, at least this many replicated runs. And in some cases, I'm also saying I want at least this many lack of fit degrees of freedom, which is a lot more complicated to
yeah,
kind of uh, enforce. But the replicated runs, you can always enforce that. And so what we end up doing is we break up a candidate design into like unique rows or like rows that we allow to be whatever. And then we have a bottom set of rows that we require to be replicates of some ones from the top.
hmm
And so it's kind of a mix of coordinate exchange, the top part, and then row exchange in the bottom part to kind of look at all different kinds of
different
combinations.
combinations. Yeah,
Mhm.
right. Clever, very clever.
Thanks. Thanks.
Yeah, that's an elegant way to really approach the problem.
Mhm.
Have you still got students working away on different aspects of this?
I haven't. So I had about 7 PhD students at one point a few years ago, and I said I need a break. So I'm getting some more right now, and I'm teaching a PhD level design course next spring to kind of recruit more of them, and I'll go over like this paper and some of the more recent papers on screening experiments.
Good, good. Well, I've been interested in non-regular designs for screening for
Mhm.
quite a while. Brad Jones and I got interested in this, oh, 10 years ago, and started looking at existing non-regular designs.
Mhm.
If you confine yourself to say uh, two-level designs and you look at say 16 runs just to pick a number, and you're interested in designs that accommodate, let's say, a certain number of factors, like 8 factors. There's a whole variety of these designs. There's like in some cases there's dozens of them.
Yeah.
And sorting through which ones of those would make good candidates for screening is kind of a challenging problem.
Mhm.
And working with him and a couple of my students, we sort of identified little batches of these designs that would be reasonable candidates for screening. And then the next trick is analysis,
Mhm.
because they do have these these complicated alias structures, and how do you do the analysis? And so we've looked at different methods. And in fact, I had a student that actually developed an analysis technique, which she calls alias informed model selection, AIMS. And
Oh yeah,
we
that just came out, right?
Yeah, but
Oh yeah.
we have one paper that talks about specifically about the
Okay.
six factor designs, and then another one that was just recently accepted, which is 7 and 8 factors.
Okay.
And in theory, you can extend this Ames method to any non-regular design. It gets a little tricky as the size of the design gets bigger. When you go to start to 9, 10, 12, as things start to get a little bit tricky. And in fact, I've got a PhD student now who's looking into how to do that.
Hmm.
And she's actually doing some preliminary work right now, which is looking at how does some standard analysis methods work for these designs. Like stepwise regression and Danzig selector, and some of these other generalized regression methods. And actually, some of them work surprisingly well, which
Mhm.
is which is which is interesting. They often do a pretty good job of identifying the right model,
Mhm.
but they end up making some type one errors. Uh,
Right. You have to accept that.
yeah,
Right.
but on
I
the other
think,
hand, my view, and I think most experimental design people would agree with me that in a screening situation, type one errors are not nearly as crucial as type two.
yeah,
Because
absolutely.
if you think something's important and it really isn't, you're going to find out about it subsequently. And
Right.
the real disaster is when you fail to identify an active factor, and that screws up your entire product or process development scheme.
Mhm.
and, and along comes a competitor that figures out that that is in fact an important factor, and you're dead.
Right.
Your system is dead in the water.
Yep.
So I don't really tend to worry too much about type one errors, but you need to try to control that if it's at all possible. I mean,
Mhm.
you really do.
Right.
And I just wondered if you'd thought much about, analysis methods for some of these designs.
So I've actually done quite a bit of work on the penalized regression
Ah,
with Maria Weiss, Byron Smucker, and David Edwards, and my recent student, Kate Young, and particularly for supersaturated designs. And the one thing that you have to worry about whenever you're using a penalized method is the tuning parameter selection
yep,
technique that you're
yep.
using. And what people will, I think the common, like kind of existing state of the art, I don't know if you want to call it that, but they use a model selection criterion like AIC, AICC, or BIC.
Mhm.
And a big part of the second part of this paper that I was presenting on was saying that if you use BIC, or this also happens with AIC, like the stock definition for it, you're almost always going to end up over selecting because the first part of that criterion is looking at the log of the residual sum of squares
Right,
divided by n. And so if you have a small run size, when you overfit the model, it can make the residual sum of squares like shoot to zero almost
right,
immediately.
yep,
And that makes the log of it go to negative infinity. And so it's just going to end up forcing it to always over select
right.
that type of model. And there's nothing that you can really do about that. So I'm not a big fan of that method. There's a new method that I'm pretty excited about from Rocky Singh. I don't know if you know her. She works with Jon
No,
Stallrich.
no.
It's actually a really clever idea, and I think everyone should be using it, is when you're using like Lasso or Danzig, what often will happen if you look at like the solution path of estimates, what you hope happens is like there's a clear separation,
Mhm.
right? And so they said what you should do is run a k-means clustering algorithm with k
Mm.
equal to 2 to kind
Huh.
of figure out how they should be
Yeah,
separated. And it works a whole lot better,
that's pretty clever.
yeah, than trying to do like a threshold for what the variance might be or something like that. So that actually works pretty well.
Well, I know what you mean about these tuning parameters. I had a master's student a few years ago that looked at using Danzig selector for some of these non-regular designs, and what we found was that your results depended a lot on how you chose the tuning parameter, and
Yep.
we came up with some sort of heuristics of ways to kind of deal with that, but I always felt like it was that what we did wasn't very complete. But she was a master student and she did a good job with that, and we left it at that.
Okay.
But,
You
but
should check out in that same issue of JQT that this paper's in. I have another paper with those co-authors I mentioned, um, where we talk about like issues with using Danzig selector and lasso
yeah,
if you're not careful, and not just the selection, but making sure that you're doing this on a dense grid of tuning parameter values. Some papers just use like 10 values of the tuning parameter, which is they kind of
not enough.
right, they like accidentally like stumble upon the sparse model like they don't realize they're kind of not like cheating, but like they're kind of uh baking in uh by not exploring all tuning parameters, they end up tending to pick a larger tuning parameter than they probably should,
Mhm.
which means they're likely getting a sparser model than what they should be picking if they like did BIC
Yeah, use
correctly.
a little finer grid
Right,
on the tuning parameter. Yeah,
right.
that's one of the things that we sort of noticed in the work that master student of mine that I referred to did.
Okay.
But anyway, this whole business of these non-regular designs and as I think of them and the associated analysis methods and how reliable they are. I think this is just a fascinating area, and there are just a lot of there are a lot of applications.
Mhm.
There are a lot of applications. My application domain has been primarily with the Department of Defense for doing operational testing because these are experiments. These operational testing experiments are these are full scale experiments with the final product.
Mm.
And so like it might be the performance testing for like the F-35, for example.
Mm.
And the experiments that you run are complex experiments in that they tend to have a lot of factors. It's not unusual to have 6 to 8, 10 factors. Runs are hideously expensive,
Mhm. Yeah.
you know, and, nobody's excited about doing 64 runs, or
No.
even 32 runs,
Right. Yeah.
how many, you ask the people in the OT community, how many tests do you want to run? One.
Yeah. One.
We want to do one. Well, that isn't going to work, so you start working your way up from there, and the other thing is sequential experimentation is almost impossible
Mm.
because you need test facilities, and so you reserve range time or equipment time or operating personnel. You have to arrange all of this in advance, and so in the classic industrial world, you run a screening design, and then you say, oh, well, we're going to do a follow-up design to help us identify these other. Yeah, right. Well, so you go back to the people that have control of these facilities, and you say, okay, I need the range again. I need the equipment, I need the people, and we're going to need to do another, 8 runs. And they say,
Mhm.
okay, we can get you those 8 runs scheduled in July of 26.
Uh-huh.
Because we're completely booked up until then.
Uh-huh.
Yeah, and so you find yourself forced into what those of us that like to think about classical screening designs hate, which is a comprehensive experiment.
Mhm. Yep.
You have
One
to
shot
get
experiment.
everything at once.
Hmm.
And that just goes against the grain of what we teach people in classic experimental design. We teach them that
Right.
screen then optimize,
Hmm.
and or screen then characterize and then optimize. We George Bach's sequential experimentation. That's
Right.
what we all believe in. But
Right.
there's just places where it does not work,
Hmm.
and so that's that's why these non-regular designs that have the potential to estimate main effects and two-factor interactions have been things that have been appealing to me for the last few years.
Right.
But this is
But
fascinating stuff, John. I really have enjoyed. I've seen these papers and I've looked. I just haven't really dug into them as much as I should have. But this is really fascinating.
so the application that I talked about with people at NC State, one thing that I actually got them to start out with running a supersaturated design
Mm,
that from a new paper that we've written that's like an optimal design actually for lasso. And they ran it. And what we ended up sort of finding out or concluding from that is that their effect sizes were not very large. And that's kind of one thing that has to happen with supersaturated designs for there to be any hope at all that your important factors have a large size.
Yes,
But it also is important for, non-regular fractional factorial designs if you're trying to do some sort of like QQ plot analysis,
right.
that you need these outliers. And that's actually one benefit of the designs that I'm coming up with, is that you don't need to rely on this sort of huge discrepancy in inert and active factors to be able to do testing. And one kind of like, I don't know if like you want to call it like a dirty little secret, but with every screening design, you kind of are saying that we'll assume you pick your high and low level so that you have a strong effect.
Yeah,
And you don't always know what those are going to be
that's right.
in practice.
That's right.
And you don't want to be faced with a situation where you could have an effect that is statistically significant, but you have no estimate of variance for you to actually detect that.
Right.
And
And
so
it could be a factor that has a very important impact in terms of how the product or the system actually works.
Mhm.
The effect isn't big, but it's important.
Right. And it's not just with testing. I mean, a good estimate of variance is important for prediction,
Sure.
right? If that's wrong, then you're you may be under-reporting how your level of confidence should be in your prediction intervals and things like. So I really do think that that is something that should be. I mean, it's hard to do this. I mean, obviously, like these existing screening designs work really, really well. People have been using them for
Long
decades,
time.
all the
Yep.
time, right? But I think there are some situations where you may be uncertain about uh, the factor settings that you've chosen.
Right.
And I think it's fine to sacrifice a little bit in terms of design variances if it does give you a good idea of what your process variance is. I mean, that should be a goal with every screening experiment, is to also characterize the process variance and not have to have that rely on your model selection procedure being accurate.
Yeah. Yeah. I know when I'm teaching my students about screening designs, and we're talking about the classical 2 to the k minus p designs. Uh, I always tell them that when you're designing a screening experiment, that you should view your job as the same mission as Captain Kirk and the Starship Enterprise. And I say, now, what was their mission? And of course, a lot of the students are too young to,
Right.
to really remember Star Trek. Okay. And I said, well, Captain Kirk and the Starship Enterprise, their mission was to go boldly where no man
Hmm.
has gone
When the man's
before. And
gone
that's
before.
what you should do in a screening experiment. Be
Hmm.
bold.
Yeah.
If you make little bitty changes, the signal is going to be overwhelmed by the noise.
Hmm.
Uh, and that analogy works well for most of my students because they're engineering students. And so signal and noise, they get that.
Right.
So you have to change the factors enough so that the signal is large relative to the noise.
Hmm.
And it said, but you may not know how to do that.
Right.
And this is a place where pilot runs can help.
Hmm.
If you have the resources to be able to do pilot runs. And I make all of my experimental design students do projects, and they have to work in teams of 3. And it still gives me a ghastly number of project reports to read.
Yeah.
John, I have 130 experimental design students this semester.
Holy moly.
Yeah, about 50 of them are online.
Okay.
And the other like 80 are in the classroom, and so going through these project reports I always enjoy it,
Yeah.
because they do interesting stuff.
Hmm.
They really do interesting stuff. Uh, I've got just a little off track, but I've got a group of students that are growing beans.
Okay.
Yeah. And they're looking at the impact of sunlight and irrigation and soil and fertile, all this stuff
Hmm.
on the height of these bean plants.
Hmm.
And they're having the best time with this
That's
because
great.
they've got gardens in like 3 different locations, so they're blocking on location. I mean,
Okay.
they've really gotten into it.
That's cool. I
Yeah,
used to do I used to do projects before COVID, and the problem that I was running in with the projects is the way I set up my class is I have to spend almost the first half just talking about analysis,
yeah.
like factorial analysis and everything. So they don't actually get to like learn about designs until the second half, and they should have already kind of started planning things by then. So I always really enjoyed it, but they would present me with their proposal, and I would tell them like, "Oh, you really need to do this as a split plot design," which we talk about like the week before the finals.
Right. Yeah, it's kind of hard to introduce that at the last minute. Yeah.
Yeah, but it was always very rewarding having everyone present. They were all very excited about it. I tried to recommend. I was like, well, just be careful if you're going to do something about growing things because
Right.
if if tomato plants if like they just don't grow for some reason, then that's
You're
not going to be a very interesting
you're
paper.
in big trouble, right?
Right. So I just had I'd have the paper helicopter experiment in my back pocket and just tell them they could do that if they needed to.
Well, most of my students have already had a calculus-based engineering stats course,
Hmm.
so they've been exposed to analysis of variance, and obviously all of the one and two sample inference topics, and given at least some exposure to regression,
Hmm.
not a comprehensive introduction, but some exposure to regression. And so we can start talking about design fairly early. And I introduced blocking very early,
Hmm.
factorial experiments fairly early, and we spend a lot of time on the 2 to the K system.
Okay.
And we get to talk about an introduction to response surfaces and mixtures, and obviously the split plots, and think that comes pretty late in the course. In fact, that's what we're getting into right now, and that would be too late to help people.
Right.
So
Yeah.
as I review their project proposals, I try to discourage them from things that involve like either nested or split plot type problems because they come up later in the course.
Right.
But
Even though they're super important.
what are most of your students? Where are they from?
So I have about half of them are from the stats department, and the other half are from very different backgrounds.
Okay,
And so I can't teach. I wish it was just a group of engineering students because then I could go straight to like mostly numeric factors,
right.
maybe some categorical ones. But no, I have a lot of people from like ag and dairy
Mhm.
science, and they just have like the more traditional like experiments where you just have a bunch of categorical factors.
Right.
So that's the way that I've decided to kind of teach the class because I think it best serves the people that register.
Well, I wrote the first edition of my experimental design book. It was published in 1976. And I tell people that the reason that I wrote that book is I had a room full of engineering students, and all the textbooks were agriculture
Hmm.
samples. And I said, it wasn't very motivating to go into the classroom and talk about an experiment with your engineering students and say, well, what if you have 4 sheep?
Right. Yeah. Right.
They are never going to have 4 sheep, right?
Right. Yep.
And so,
Yeah.
I had to do something, and so writing the
Right.
book was the answer, and it's worked out pretty well. It's now in the 10th edition and seems to be doing okay. But
Yeah, I think you're doing all right.
at any rate, I really appreciated this talk, and a chance to chat with you about this has been fascinating. But maybe we ought to see if there's anybody else out there that has a question or
Sure. Yeah.
wants to talk with us. I don't know. Let's see if I see Nikki is poring over the computer here.
No, no question.
Okay, we've solved the problem, John.
I guess so. It's one of two possibilities.
Well, as I say, this has been a really pleasant talk. I've really enjoyed this, and I think that you're doing some really fascinating work. And if you see any chances that we might collaborate down the road, keep me in mind.
Sure.
I'd be
Absolutely.
interested in working with you. You're doing some really interesting things, and I've collaborated some with Maria Weiss and that crowd out there, they do some really interesting things, I think.
Yeah. I worked with Brad quite a bit as well. He was on my PhD committee.
Ah, okay.
So,
Yeah, Brad and I have been collaborators for a lot of years,
mhm,
and I don't see as much of him since he's retired.
right.
But he is, I think, planning to come out here first of the year. He and Naksham and I we've been working on a paper for like 2 years. We've
Oh,
decided we need to finish it.
I get that. Yeah.
Yeah, we've decided we need to finish it before one of us either dies or all of our mental capacity goes away, and
Mhm.
we need to get the paper done. So I
Right.
think he's planning to come out here, and uh, Chris comes out here a lot in the winter.
Okay.
He has a vacation home out here.
Oh, okay. Yeah, I guess
And
he's in Minnesota, is that right?
yeah, yeah.
It's kind of
And
cold up there during the winter.
he likes to escape the snow and the nasty weather in Minnesota, and come out here, for a few weeks every winter, and
Mhm.
he can arrange his schedule so that he's able to do that.
That's nice.
I met him when he was a student
Hmm.
at Minnesota, and it was an interesting situation. I was at Georgia Tech as a faculty member, and people at the University of Minnesota asked me to interview for the job of department head
Hmm.
of industrial engineering. And I had no desire to be a department head, although I ended up later on as a department head at
Right.
Washington, which was really stupid. Talk about making bad decisions.
Right.
But I had never been to the University of Minnesota, and I said, "What the heck? I'm going to go." And uh, first of all, I should have figured out they weren't really very serious about me. Okay, because they arranged the interview in January.
Yeah.
And for a guy from the South, going to, Minneapolis in January, talk about a shock.
Right. Yeah.
I thought I was going to turn into an ice cube.
Yeah. It
It was
gets cold in
brutal.
Blacksburg, but not that cold.
Yeah. Blacksburg is cold and windy.
Yeah.
Yeah, it can be incredibly windy.
Hmm.
I can remember as a undergraduate student marching along that drill field, and
Hmm.
being absolutely blown sideways by like 50-mile-an-hour winds.
Yeah.
Brutal. Can be really brutal. Well, I guess we're at the point that since there's nobody bugging us
Hmm.
with questions, that we can log off, and
Okay.
you can get a minute or two of your day back, and I can dash off to my next meeting. And I hope you have a really productive rest of the year and nice holidays.
You as well. Thank you very much for the invitation.
Well, glad to have you, and I may in fact ask you to come back for a repeat engagement at some time. I do invite people back if I think their topics are really interesting, and this is fascinating stuff. And so I don't be surprised if I try to lure you back again sometime, maybe toward the end of next year.
Sure, absolutely. Just let me know.
Thank you.
You're welcome. Bye.
Bye bye.